All right, welcome back everybody. This is the second to last video in this playlist. I'm going to be going over some exercises that are designed to help you understand and develop the models that were given in the examples. So for the resistor model, I'd like you to take the initial values of the initial state being 100 ohms, a sigma of 0.1, and an initial covariance of 0. Then I want you to start the recursive loop with the gain equation first and run through the loop 3 times. Now if you don't want to do it by hand, you can use the models that are out there, the Python code. For the second problem, for the resistor, I want you to consider how the measurement model would change when you add a second voltmeter measurement. So we're talking about the Kalman filter implementation of the resistor estimation problem. So the second voltmeter will be measuring the ohms also, but it'll have the identical characteristics statistically, so identical accuracy. Then consider how it would change the measurement model if the second voltmeter were not exactly the same, but were perhaps less accurate by a factor of 2. Finally, I want you to modify your own copy of Run Average Demo and add a small amount of process noise to the truth model. And then compare how well the running average performs compared to the Kalman filter in the KF resistor demo Pi file using statistically identical process noise. For the constant velocity motion model, I'd like you to calculate the Kalman gain of the non-acceleration motion. Here's a hint. It should look a lot like the gain for the damped harmonic oscillator. Then I'd like you to modify the measurement model for this constant velocity motion model to add a second sensor, which is a velocity sensor. So we'll have a position sensor as we did before, but then an additional sensor that's sensing velocity directly. And then ask yourself, how do the dimensions of the Kalman gain matrix change after modifying the measurement model in this way? And then if you run the simulations, you can figure out how much the RMS accuracy will, or the RMS error will change, but both for the velocity estimation and the position estimation after the addition of the direct velocity sensor. Next we come to the damped harmonic oscillator, and the first thing I'd like you to do is modify the measurement model so that you have, again, a direct velocity sensor, just like you did for the constant velocity motion. And then ask yourself, how much does the RMS error accuracy change for both the velocity estimation and the position estimation? And then create a second sawtooth plot so that you can take a look at the velocity state estimation sawtooth and see how that pattern changes with the addition of a new sensor. And that will do it, but that's a pretty good list of 11 exercises. In the next video, I'll be talking about their answers. And that'll do it for today. So we'll see you in the next video.